Okay, so video one left off here with this example problem and just how we've defined our extrema on our three-dimensional surfaces. So we are going to look at something that is going to make this a little easier and also open up some different possibilities of what happened with our extrema. That is called the second partials test. So this is the min-max theorem. We have the second derivative test in calculus that, like I mentioned in the last video, covers concavity. So second derivatives do tell us all about concavity. Here, our second partials test tell us how this acts on quadric surfaces, okay? So again, we're using this definition from the extreme value theorem that says my first partials are set equal to 0 to find those critical points. And this second partials test says that where that occurs and we get those critical points, we can test them for relative extrema using this formula right here. So like in the last video, we looked at our second partials and we were able to generalize. Here, we are going to actually specifically find a value for our discriminant. So that is what D represents here. We are going to find the discriminant, and there are actually 4 different possibilities. So that's why I say this opens up a few possibilities for us. So possibility number 1 is that I find the discriminant using my second partials test right here and plugging them into the formula and doing all that stuff. And I see that my discriminant is positive. It's greater than 0. But what has to also happen is that when I take those second partials, so both with respect to x and y, that they were positive as well. So now, even though we didn't look at the discriminant in the example that we ended the last video on, and we didn't find this value for D, we did generalize that our second partials were both positive, and we saw that we had a relative min, or we just called it a minimum. Okay, but that is in fact the case here, that if that happens and you find your discriminant, and in the process of that, each of those second partials were positive as well, that we have a relative min. Now you see where this could fall apart if both of them are not the same sign. That could be an issue, right? And this is why this opens up more possibilities, but we'll get to that. So my second possibility here is again that the discriminant is positive, greater than 0, but what happens is each of those second partials is negative. So again, they are the same sign, okay? Now you could again just look at the second part of this statement. If both of those second partials are negative, then we can generalize a little bit. We know that we are going to have a relative max, and my screen here. Okay, get that back. All right, so sorry. So the second piece of this, we can generalize, and we know that that critical point will occur at a relative max because those second partials are both negative, which means concave down everywhere along x and y. All right, so now what happens if the discriminant is not positive? Let's look at that possibility first. If it's the case that I calculate the discriminant and it's not positive, it can't be a relative min or max, what else can it be? Well, we can actually stop there. No second part to the statement. If it's negative, we have what's called a saddle point. So we can go back to our notes on quadric surfaces and see that at a saddle point, we would have concave up along one axis, we would have concave down along the other axis, and we would get literally what looks like a saddle. So I would get maybe something like this, where in the positive x direction here, we would see that, or I guess anywhere in the x direction, we would be concave down. We see that that concavity is pointing down. And in the y direction, anywhere in the y direction, I would get concave up. So I'm evaluating this critical point right here at 0, 0, 0 and seeing that I am sitting on a saddle point. And that's what happens when the discriminant is negative. Okay, now the last option here is what happens if the discriminant is equal to 0. Okay, well, that would be a situation that we would consider inconclusive. That could be because, you know, we had like that first example with the cone in the last video, and you can find those first partials, but you get, 0 over 0 when you evaluate at that critical point, or some 0 in the denominator, something like that would be inconclusive if D is equal to 0. Now, the one thing I didn't point out is, these second parts of the statements here, where my second partials always match in sign, they're either both positive or they're both negative. And I didn't talk about, well, what happens if they're different signs? Well, if they are different signs, what is going to happen is your discriminant will be less than 0. That's why there's no second part to that statement. So I kind of skipped over that. But you will see when plugging it back into this formula here that if f partial xx, f partial yy are different signs, you will get a discriminant that is less than 0. Okay, so we're going to do one example of this together and in this video, and then you let me know if you have any further questions as you're working through the assignment. We're going to do this example right here. So our function g of xy is equal to x squared minus 4xy plus y squared. So first things first, as always, we have to identify our critical points. So we are looking, so step 1, we are looking for where our first partials are simultaneously equal to 0. So you can pause and figure out what that would be, and then go ahead and play when you're ready. So my first partial with respect to x here is going to be 2x minus 4y. Little trouble in paradise here because I have a function of both x and y still. When I take the first partial with respect to y, I see the same thing happens, negative 4x plus 2y. So we have a bit of a system here that we have to solve simultaneously. 2x minus 4y, we want that to be equal to 0, and we want negative 4x plus 2y to be equal to 0. So we'll do a little process of elimination here. I'm going to go ahead and multiply my top equation by 2. I get 4x minus 8y is equal to 0 when I do that. And then negative 6y is equal to 0, or y is equal to 0. So there's a y value. When I plug that y value back in, I'm just going to go ahead and plug it into partial y here since that's closest. So negative 4x is equal to 0 if I plug in that 0 for y, and so that means x equals 0 as well. All right, so I found a critical point, a single critical point. Now you see, now that we're solving systems, we got linear equations here. Where you come up with more critical points is potentially when you have quadratics left or something like that. So in this case, a single critical point, though that may not always be the case as we start adding some more powers into this and we get things like quadratics. So here's my critical point at 0, 0. I'm going to go ahead and use the second partials test here. So step number 2, we are going to test our critical point. And as a reminder, we find the discriminant by taking our second partials. Don't forget that our f partial xy is squared. And I guess this function technically is g, and I've been writing f. I don't even know why I went with g. I mean, we do everything in terms of f. So I guess the easier thing here to change would be to say this is f of xy. My bad. Sorry about that. All right. Now, a good thing to do, and here it doesn't make much of a difference. We have our single critical point, but I will show this to you because sometimes it does make it a little easier when you have multiple critical points, is let's just list out everything. So we're going to do this in table form. So what's the x of my critical point? What's the y of my critical point? What is my second partial evaluated at that critical point? What is my second partial of y evaluated at that critical point? And then last but not least, my mixed partial, f partial x, y. And then we'll go ahead and using the formula right here, we'll figure out what is the discriminant. And then finally, what is the result of that? So again, here doesn't make too much of a difference because I'm just testing my singular critical point. But this could help when you have multiple. So what is the x? It is 0. What is the y? Also 0. If I take my second partial with respect to x, I'm going to zoom back out here a little bit so I can see my first partial. All right, so my second with respect to x, oh, I got lucky. It's just a constant. So again, if you have something that is still a function of x or y, make sure that you are plugging in the critical point of 0, 0 in for any x's or y's. But here I got lucky with my constant, so that is just 2. I take my second with respect to y, and the same thing happens. I just also get a constant of 2. So there's that. Now, when I do my mixed partial, so I'm going to take f partial xy. And for that, I do get another constant of -4. All right. So we've got all of that, and now we're going to plug that into our formula to find our discriminant. So it looks like I am taking 2 times 2 minus a -4 squared if I'm plugging everything in. So I'm going to get 4 minus 16, which is negative. My discriminant is less than 0. Okay, so I can stop there. My discriminant's less than 0. This must be a saddle point. That's the result of my second partials test. So the nice part about this, not only when you have multiple critical points to test that it lays everything out, but also, if I got that my discriminant was positive and then I have to go back and I have to look, okay, what are the signs of my second partials here? Then that's also just kind of laid out pretty easy to find. So that's the second partials test. Again, hopefully it makes things a little bit quicker when we are finding extrema and trying to categorize them.